Alright, today we're going to look at some more list functions. Lists that turn out to be very useful in Haskell, and we'll explain why we use lists so much later on. So first of all, here's a few predefined list functions. If you look at list.2.hs on our link, then you can find these definitions of these. These are all useful things that we have to sometimes use. So first of all, you could write just E1 to En as a list of elements from E1 to En inclusive. So if we just do this list, let's start GHCI. If I just go 2 to 7 as a list, it's going to tell me 2, 3, 4, 5, 6, 7. Okay. This is pretty extensible. You can do E1, E2 to M as a list of all elements from E to 1, where this is a step size. So we could go 2, 7, ... 33, and it's going to give me all the lists of 2, 3, adding up all of these until it gets this. So this difference between 2 and 3, this is going to step by 5. Okay, so if I went 2 and 4, if I went 2 and 8, for example, that's going to step by 6s. Okay. Notice that this is the same as if I did 2 to the 6 to 35. So it just stops it when it's before then. Okay. E dot's a list of all numbers from E. Alright. Turns out this is the one that's the infinite list of numbers is actually very useful. And one of the reasons it's useful is we can do something called take, which just takes the first element of the list. So I can do take I can just take 5 from 2, 7, ... is the infinite list of things. I'm just taking the first 5 elements of it. So although this becomes an infinite list, it just takes the first 5 elements off. It never actually computes the rest of the list. The things you might want to do are things that people in other languages tend to want to do, is to take the head and the tail of a list, or to find the nth elements of a list. This is in Haskell, so you can actually do heads and tails, and you can even find the nth element of a list. However, whenever I read Haskell programs, it's very rare to do this. Hardly anyone takes the head and use head and tail, and even the exclamation, getting the nth element of the list, is also a very unusual thing to do. It's not sort of something common. We much more like giving just pattern matching. Okay, and it's very unusual to want to take the nth element of the list, because we have other ways about going through a list than just counting through them. Okay. Things that are very common are plus for append. So if I can do 2, 7, ... 22, and append that to 1 to 5, I end up with what you might expect. And we can sum that. The other thing you should know is there's something called it, which is it's the last thing to do. And I can do sum of it, and it tells me the sum of this list. Okay, so if you want to do some elements, we're going to write sum of the list, and it sums over all the elements of the list. One thing that is very useful is a zip function. Okay, so we can zip these two things here, and we end up with something else. So we can do zip. Let's do zip the list containing quote A to Z to right, that's all the letters from A to Z, and we're going to zip that with one infinite list of numbers, and we end up with this. This tells me for each letter of the alphabet what the corresponding number is. Okay, so it works just not for numbers, but also works for other elements of the letter bolt. And I can do zip zip 0 to 1024, and I can then do the list of all the characters. So it turns out that's the very first ASCII character. I get the infinite list of all of them. I don't know what the first 1024 is. It tells me each of these numbers, and they're not very interesting, except when you get early on in this list. Maybe it's only the first 128. So it tells me all of the ASCII code. So here's gives me ASCII code. So capital D is 68 in ASCII code, and B is 66, and left parenthesis is 40 in ASCII. Okay, so it does all of these things. Maybe there's only 128. Okay, so I did it for all of them. 128. Okay, so I can do that. So that's what I did before. This list of, so 0 to 128, this has essentially infinitely many of them, or arbitrarily many is how many there are in how many characters there are in whatever character code is doing. And this is sort of giving us, so it only does it to the number of things that we're going to use. So whichever one runs out first, so this one here runs out first, that's what we're going to use. Okay, zip turns out to be very useful. Okay, much more useful than you might think. I'll also explain why later on. Another thing that's useful is things like map. So map is a function that applies a function to every element. So map of +3 to the list 1 to 10 adds 3 to every element. So it turns out map is also a very, very useful function. Okay. All right, one of the things you might want to wonder how to do is, well, how can we find the first elements of the list that are less than 3 or greater than 7 using filter? Well, you might want to filter it twice and then append them, but we can do much more interesting things than that. And that's to use this thing called lambda. So lambda is from the lambda calculus. And lambda lets us define a function without giving a name. So here's a function. It takes one argument x, and it returns true if x is less than 3 or if x is bigger than 7. Okay, so that's where we read this. So this is a lambda. And now we can do filter. We can do filter, here's my lambda expression. This returns the x, such that x is less than 3 or x is bigger than 7. So it's going to select those elements from this list of 1 to 10. Okay, so we can do this. And we can get 1, 2, 8, 9, 10, because they're the numbers in 1 to 10 that are less than 3 or bigger than 7. All right, so it turns out that when we write a definition like foo of x equals expression, then that's actually equivalent to writing foo is equal to lambda x goes to expression. So foo is just a value, and the right-hand side here is a function. So these are both syntactic variants of each other. So these mean exactly the same, and you can use whichever one you like. So we can write foo of lambda x goes to foo has the value as a function, given an x returns this expression, or we could just write it in this way as well. We usually write it in the highlighted way now because it's easier to read. And we can write down foo of xy is equal to an expression. We can write that in this way. Given an x, it returns a function from y into an expression. So that's how we're going to read that. So foo is this function that given an x and a y returns an expression. And we can write it this way. Foo is given an x and a y, you evaluate it to the expression. So all of these three are exactly the same thing. In fact, it's the same thing we're going to write in here. Okay, and here's how you might write add. My add is lambda xy goes to x plus y, and if you do this, you find my add 4 and 7, you get what you expect is 11. All right. So another thing that's useful is what are called list comprehensions. So in mathematics, you might be very familiar with writing a set of x squared, such that x is an element of the first numbers 1 to 7, and x mod 2 and x is odd. So x mod 2 is 1. So in Haskell, you'd write that in a very similar way. You're going to write the list, so it's not just a set here, it's the list, of x squared, such that x is in the elements of 1 to 7. So this funny arrow here is meant to be element of. And this comma here is and, so next mod 2 is 1. And this is called list comprehensions. So list comprehensions is this. So here's a x squared such that x is in the 1 to 7. And it's doing this. And it's mod. Whoops. It's got to be backward case mod of 2 equals 1, and it's because copying PDF doesn't copy the right character. And we get 1, 9, 25, and 49. They're the squares of the odd numbers from 1 to 7. Okay. Now it turns out list comprehensive are just a mix between a filter and a map, right? So it filters by this, and this corresponds to the map. So sometimes they're much easier to read than a filter and a map put together, because it sort of incorporates the lambda as well. So it incorporates the fact we've given this thing a name, and now I can refer to it here in the filter and the map. So it's like a mixture between a filter and a map with a lambda. And it can also do pattern matching. So you could do, x plus y, the list of x plus y, such that, x is in that thing, and it's going to tell you the sums of the lists. That's 3, 7, and 11. Okay, so it's x plus y such that the pair of x, y is in this list, and this is sort of a common thing to do. Remember, this was constructed by a zip. And we could try it all the ones where x is less than y. So here's this run on the right hand side gives us a condition here, and the ones where x is less than y are ones, it includes this one, but not the 4, 3. So you just get 3 and 11. Okay. So here's an exercise to think about before class. We'll do this in class. Is implement the dot product of A1 up to AN and B1 to BN. And the definition of it is you're going to point-wise multiplication of A1 times B1, A2 times B2, and you can add them all up. Okay. So hint, you can do this with in terms of a zip. So the zip that we saw before was very useful in that. All right, so that's some useful syntax and some useful functions that we're often going to use when we do lists. All right, thank you all.